For decades, adopting a model-driven framework meant locking your organization into a rigid interface. Now, that monolithic approach is breaking apart into multiple, fluid paths. Every model-driven framework asks the exact same question early in its lifecycle. The answers cluster around three options. Programmer DSLs offer absolute precision but exclude non-engineers. YAML is universally accessible but visually flat and sensitive to indentation. Visual editors provide intuitive spatial geometry, but become inefficient for text-heavy work. Picking one of these surfaces meant accepting its consequences for the next decade. The framework built the ecosystem around that specific format, and every team member had to adapt to it. But the authoring surface does not need to be a permanent framework-level commitment. It can be a transformation pipeline declared at the resource level, with the format chosen per file, per author, and per problem. By separating the underlying semantic model from the tool used to write it, teams maintain total structural rigor without forcing subject matter experts and engineers into a single, compromising interface. If you want to uncouple the interface from the model, Markdown is the optimal default format to serve as your base substrate. First, large language models are natively fluent in it out of the box. Because they have consumed countless GitHub readmes and technical blogs, the output they naturally produce is Markdown-shaped. You do not need to teach the model a custom syntax through extensive prompt engineering. Second, subject matter experts already use it daily. Knowledge workers write Markdown in pull requests and design documents. They can draft structured models using simple text conventions, like headings for element types and lists for attributes, without having to learn a programming language. Third, metamodels themselves can be authored in Markdown. The documentation for the format acts as an actual instance of the format, allowing it to scale across domains without requiring per-model tooling updates. The mechanics rely on file name pipelines, like myproduct.pm.md. The extensions assemble a transformation chain. It loads through a Markdown factory, passes through a .pm filter, and emerges as a structured EMF model. From the client's perspective, this complexity is invisible. The code executes a standard resource command, and the framework hands back the target model. Markdown succeeds as a substrate because it bridges human intuition, machine generation, and strict structural mapping in one lightweight text file. Markdown handles prose well, but complex systems require different types of representation. The framework does not need to enforce a uniform format across the entire project. This graphic illustrates multiple file formats mapping to their strengths. You see Excel capturing tabular data, Markdown handling prose, and Draw.io managing spatial geometries. You can author a C4 model as a Draw.io diagram, while descriptions are written separately in Markdown. Downstream, they converge into the exact same structured EMF target model. This federated approach reverses the traditional relationship between tool and user. The framework adapts to the specific nature of the work being done, rather than forcing the user to adapt their work to the limitations of the framework. This flexibility extends directly to live APIs. Organizations rely heavily on systems like Confluence or Notion, but these wikis lack the semantic snapshot capabilities that Git provides for source code. They are treated as mutable, evolving documents. Instead of migrating that existing content, we use progressive formalization. Wiki pages are structurally mapped to a formal model. Page titles become element names, and structured sections become features, without altering the source material or disrupting how teams currently write. A REST API resource factory consumes the live wiki URI, processing pages and links to produce a typed EMF model. Saving it yields an immutable, version-controlled artifact for semantic diffing. Instead of just highlighting added text, the system detects exactly when a specific component gained a new architectural dependency. Teams continue using their wikis exactly as before. Behind the scenes, those text graveyards are transformed into queryable, version-controlled strategic assets. Because the content flows through a transformation pipeline, the framework can dynamically control what data reaches the end user. The contents filter uses a security principle to determine exactly what information to project into the output model. Take a single source file. When loaded, the framework identifies the requester, a human executive or an AI agent. The filter projects entirely different views. The executive receives the complete strategic portfolio graph, while the AI receives only a strictly scoped, restricted slice of that graph relevant to its task. The data access boundary is constructed identically for both humans and machines at the resource set level. This eliminates the need to write and maintain fragile access checks scattered throughout your application code. Currently, Markdown EMF models and resource loading compositions are fully deployed. Bi-directional editing, where a projected model can save edits back to the source file while preserving its original visual geometry, is the next capability on the roadmap. Security policies and audience projections become intrinsic, auditable artifacts of the model itself. The final layer of this architecture connects the file-level transformation directly to the tooling ecosystem by composing these file name pipelines with command-line interface command pipelines. Look at this specific CLI invocation. We have NSD model internet banking system.c4.md HTML app site. Two distinct grammars intersect here. The file name grammar in blue instructs the framework to load the text and parse it into a typed C4 structural model. The command grammar in green immediately consumes that model, transforming it into a fully rendered HTML website. To see exactly how these resource loading compositions are resolved in practice, you can review the provided documentation, explore the template repositories, and examine the NAS-Danica capability framework. The structural rigor is maintained exclusively by the model layer. The format you use to author the data is entirely variable. The authoring surface is no longer a single monolithic decision that defines your engineering ecosystem for a decade. It is simply whichever instrument best fits the specific piece of work in front of you.